All right, welcome back to the final session of the first AMP Camp. And we'll start this one off with, this whole session is focused on practical applications by real users of badass technologies. We'll start with Adam Oliner, who is a postdoc in the AMP lab working with Jan. And after Adam, we will hear from 3 representatives from actual projects that are outside of the AMP lab working with the stack. So, Adam?
All right, thanks, Andy. So I'm going to be talking today about a project called Carat, which is about detecting and diagnosing energy misbehavior on mobile devices. This is work with Anand and Jan here in the AMP lab, and with Emil and Zazu at the University of Helsinki. So mobile is a hot topic, sometimes literally. So this is an article from Lifehacker, where a user is complaining that the cell phone that was supposedly idle while in their pocket was actually apparently doing something and generating a great deal of heat in the process and running down their battery. So this is probably an experience if you have a smartphone, which is more or less everyone at this point. This is probably an experience you've had. You wake up and your battery is fully charged. You do some work. Well, maybe you don't initially do some work, but eventually you do some work. Maybe make some slides or something like that. And a lot of the time, your phone is sitting idle in your pocket. And at some point, you take it out, and you discover that your battery has been depleted. So I assume this is familiar to a lot of you. And as a user, you have 3 primary questions here. The first is why your battery is draining. Was it an app that you ran? Was it something that you were doing in the app? Is it a configuration of your system? You also want to know whether that behavior is normal. So if you were to go through the same routine tomorrow, should you expect the same result? If you change something about your device, would you expect the same result? For example, should your friend, if they ran the same app, expect that they would have bad battery life as well? And as a user, of course, you'd like to know what you can do about it. Is there something you can change about what you're running or how you're running it that would make your battery life better? So this energy bugs on mobile devices is still a relatively new area. So far, all of the approaches fall into one of these categories. There's been some work out of Purdue about looking for specific kinds of energy bugs. And these have been ad hoc approaches where they would look at the source code and try to find particular patterns of misbehavior. Most of the approaches are intrusive in some way. They require modifications to the operating system or to the code of the applications that you're trying to debug. And if you look on the app stores, you can find dozens, at least, apps that are claiming to give you information that will help you improve your battery life. And almost universally, these give you generic advice like kill all of your background apps or dim the screen or in some other way kind of use the nuclear approach to trying to improve your battery life. And of course, none of these really are telling you what was going on in the first place. So our approach is different. It's a collaborative approach. So this is the infrastructure that we use. We take devices, stock devices running in the crowd, and we have a mobile app that users run on those devices. And these apps send us instrumentation data from the mobile devices, like tablets and smartphones. We run an analysis written in Spark that's running on Amazon's EC2. We have data that's stored in both Dynamo and S3 for various purposes. And the result of this analysis are actions and reports that we send back to users. And these actions and reports they answer exactly the questions that we posed earlier. What's using up the battery, whether or not that's normal, and what users can do about it, as well as some other things. So as far as we're aware, this is the first collaborative approach to diagnosing these kinds of energy problems. And the fact that it's collaborative is important because if it's not collaborative, you fundamentally can't answer questions about whether something is normal. So that's something that we can do that, as far as we're aware, no one else can. So we do this using a mobile app called Carat, which we wrote for iOS and Android. And it provides personalized energy debugging. So what that means is it'll tell you, for your particular device, what is misbehaving, whether that's normal, what you can do about it, and how much it will help. So what that looks like, these are some screenshots from various versions of Carat. The first 2 are from what we call the Actions tab, and that's the main screen of Carat. What this is telling you are various actions that you could take that would improve your battery life, and it tells you how much you should expect it to improve that battery life. So for example, it's suggesting that if you kill Pandora, you can get another hour and a half or so of battery. And similarly, you can upgrade the operating system on this particular device and get another 45 minutes. We also have something called a J-score, which gives you a sense of how your battery life compares with other similar devices. So this is a percentile, so what this means, a J-score of 64 means that your battery life is better than 64% of similar users. OK, Okay, and so this is sort of a couple of the screens, and there are various other things that you can look at that I'll explain a little bit later. So what I'll be talking about today is how Carat collects data, how it generates the results that it generates, mostly what you saw there, as well as some other information that we're currently computing but which is not yet reflected in the client apps, which have to do with quantifying our uncertainty. So we actually know things about an hour and a half plus or minus how much and with what confidence and so on. And I'll discuss that today. And finally, I'll tell you about some real-world deployments of this technology. Okay, so first I'll talk about the Carat sampling. So periodically, the app is given CPU time to take a sample of the state of the device. And crucially, the things that it writes down are the time, the battery level, and then a feature vector that includes things like which apps are running and whether certain features of the phone are being used, like whether or not you have Wi-Fi access and so on. And so over time, Carat takes a sequence of these samples on a particular device. And some of these features may change, and the battery may be depleting. And then at some point, we want to say not just what the battery levels were, but how fast the battery was discharging. We're more interested in discharge rates than we are with particular battery levels. So we look at consecutive samples when the battery was discharging. We look at the difference in time and the difference in battery level to compute essentially a discharge rate. And there's a little bit more going on here that I don't have time to talk about today in order to actually get an accurate sense of this discharge rate. But suffice it to say that we have a way to compute this. And then furthermore, we look at the features of the two samples and generate this feature vector for the rate. And so what we have here is a discharge rate conditioned on some set of features. So we can plot this as a probability distribution. It says, given a particular set of features, what is the rate of energy drain? And to be concrete, let's say that we're particularly looking at the feature of whether or not the Facebook app was running. So this is the distribution of energy drain when Facebook was running. So we can compare different feature distributions to each other. So we could also ask then, what does the energy discharge look like when Facebook is not running? And so if you see a pattern like this, where it shows that running Facebook seems to statistically use more energy than not running Facebook, but running a variety of other apps, meaning all the other potential ones, then we call this an energy hog. So what this means is that if Facebook were categorized as an energy hog, then that would mean that statistically it seems to use more energy than most other apps. Now, we might also want to ask not just Facebook in general, but Facebook running on a particular device. So let's say we want to know the behavior of Facebook running on Jan's smartphone. And so we could build this distribution. And crucially, if we didn't have the crowd, if this were not a collaborative approach, we'd have no way of saying whether or not the energy use that we're seeing on Jan's device is normal. If we do have the crowd, however, we can make the same sort of comparison. We can compare these distributions and say whether or not this is surprising. So in this case, we would call this sort of a pattern an energy bug. So if an app running on a particular device uses significantly more energy than when it's running on other devices, then we call it an energy bug. And these are sort of very kind of gross comparisons, right? So I'm giving you just two categories of ways that we classify these apps because we found them to be useful. Now, what I've described so far are ways of just comparing these distributions. So in particular, what we're comparing are the expected values of these distributions and looking at the distance between them. And that's how we get the numbers that you saw on those screenshots that say how much improvement should you expect to get if you perform these actions. But there's actually more information that we have here. And this goes to quantifying our error and uncertainty. So in particular, we could look instead at the distribution of those means. So it turns out that those are normally distributed. And so you can look at the distribution of the means and then further say something about their shape. So we know what the expected value is, and then we can also draw these error bounds. So if we wanted to have 50% confidence, then we would encompass 50% of this distribution, and we have some plus or minus discharge rates. And we can say that the expected value is this value plus or minus some error E. And if we wanted greater confidence, then we can expand those error bounds, and we would have some larger error E if we wanted 95% confidence, say, instead. So it's important to understand what factors contribute to having a particular confidence level. So mathematically, there are only two things that matter. One is the variance of the original energy drain rate distribution, and the other is the size of the crowd, basically how much data do we have in that distribution. And so, understandably perhaps, the less variance you have in this original distribution and the more data that you have, the smaller your error bounds, the greater the confidence you have for a given error. And the converse is also true, so if you have a higher variance or a smaller crowd, then you have larger error bars. But we'd like to do more than just quantify the error and confidence. We'd also like to somehow improve it. We'd like to get more confidence and less error. And so to do this, we do forms of classification. And I'm describing all the math here in cartoons as opposed to giving you equations. Suffice it to say there's a lot going on behind the scenes. I'm hoping just to give you an intuition for the kinds of computations that we're performing here. So to do this classification, we might decide that a particular distribution we want to split into two other distributions. One that has a particular feature that's conditioned on a particular feature, and the other that's conditioned on its negation. So F and not F, say. Now, by virtue of doing this split, for both of those distributions, we're going to have less data. So we're already reducing one factor that causes our error bounds to grow. So this might initially seem like it's not a good idea. But if this split turns out to be profitable, what that means is that the variance of the resulting distributions is going to be decreased. And it will be decreased significantly enough that we have greater confidence or lower error, depending on which we're going for. But if that's not the case, then we don't do the split. So essentially, we only do the split if the result is that we have more confidence in the numbers that we're computing. So you can do these splits on a variety of features, and you build up essentially a diagnosis tree. So what this allows us to do, and again, we haven't rolled this out to the client apps yet, but we have the capability of giving a more fine-grained diagnosis than just saying, if you kill Pandora, you'll get this many minutes more battery life. We can also say things like, well, if you kill Pandora, for example, I don't mean to pick on Pandora, if you kill some app A, then you'll get X plus or minus E of battery life with 95% confidence. And we can also provide supplementary actions that you could do instead. So upgrading the operating system to another version, and we could even say what the error and confidence bounds on that are, and so on. So we can do this sort of diagnosis that's specific to a particular device under specific conditions. Say things about whether turning Wi-Fi on or off will help, and so on. So several months ago, I think back in March or April, we did an initial deployment just for the iOS version using TestFlight, which is an over-the-air beta service. Apple caps you at 100 signups, and of the 100 signups, we had 75 people install it. So we collected data for a couple of weeks. We got about 10,000 samples from this community. And the initial results were very promising. So even with just 75 users, we found 35 instances of apps that seemed to be exhibiting energy bugs. And these were popular apps, so things like the Facebook app, Kindle, Flipboard. And for all the energy bugs that we looked at, we were able to corroborate it with things like forum posts, news articles, and data correlations. And I'll describe a couple of examples of the energy bugs that we found in a moment. We also did some synthetic bug injection as a sanity check. So we instrumented the Wikipedia mobile app with 3 different kinds of energy bugs that we could trigger independently, distributed it out to a subset of the community, and tested whether triggering those bugs was something that Carat would detect. In all cases, Carat only said that the buggy instances of the Wikipedia mobile app were the ones in which we triggered bugs. Okay, so it was completely accurate, no false positives. Okay. So this was all very promising. It was a very small community. Let me tell you about a couple of the bugs that we found. So Flipboard, if you're not familiar with it, is what's called a digital magazine app. So this aggregates data from a bunch of different news sources like your Facebook feed and CNN and so on, and presents it to you in a pretty interface. And so in this 75-user deployment, it was reported that Flipboard was a bug on 6 of the clients. There was a support thread that we found that suggested that there was a particular problem with an interaction with iOS 5.01. And it turned out that those 6 clients running Flipboard were exactly, where this was reported as a bug, were exactly the clients that were running iOS 5.01. None of the users running a different operating system saw this reported as a bug. Then this was something where if you were just to upgrade the operating system, you could continue using Flipboard, and you would get 45 minutes more battery life. We also found a bug in the Kindle app. So Kindle is an ebook reader. I think most of you are probably familiar with Kindle. It has the feature that if you have multiple Kindle devices, that it will synchronize your books and bookmarks and annotations and so on among those devices. And it uses a protocol called WhisperSync to do this. So it turned out that Kindle was also reported as a bug, this time on 5 clients. And the forum seemed to suggest that there was a problem with WhisperSync that was specific to whether or not Wi-Fi access was available. So it said basically that if WhisperSync were trying to operate over the radio and not over Wi-Fi, that it used significantly more energy than if it did have Wi-Fi access. And this was confirmed by the data. The users on which it was reported as a bug did not have Wi-Fi access universally, and all of the clients where Kindle was running and they had Wi-Fi access were not buggy. And this was a more significant bug, so you could get an hour-and-a-half improvement by just turning on Wi-Fi and otherwise not changing your behavior. Okay, so this was all very promising, and then in the middle of June, we had been in the process of developing an Android port, and we finally got on the App Store after only 104 days since initially submitting. And so we were finally on the Google Play Store and the App Store, and we got featured in TechCrunch a couple of days later. And this was pretty cool, and we had talked about scaling, and we said, you know, we're going to have to deal with probably a few hundred more users, maybe even a few thousand. And you know when you do that like pie in the sky number, you're like 10,000 users, and like if we can scale to 10,000, we should be good. Well, so this TechCrunch article triggered a sort of viral thing. So we also were featured on Lifehacker and dozens of other places. And in the first 24 hours, we had more than 100,000 signups. In 48 hours, we had 200,000 signups. And now we're at about 1/3 of a million devices. So I think by the end of the day, we'll be pretty close to 1/3 of a million. So this took us by surprise, as you might imagine. So about 190,000 of these users are iOS, 190 on iOS, 130,000 on Android. We have about 20 million samples from these devices over the past 2 months. And already in the data, we've seen 20,000 apps that seem to be hogs and more than 2 million buggy instances. And we're only just now getting to the point where we're starting to look in depth at some of these. So yeah, so this was kind of exciting. We learned a lot from this experience. So I just wanted to share a couple of the salient lessons in this experience. So the first is that the cloud does not mean free scaling. So this is important because if you're trying to decide what sort of tools and infrastructure you're going to use when you want something that can scale well, it's important that those tools were made by people who thought carefully about what the right abstractions were and what the right things to reveal to the user are. What's necessary? What knobs do you still need even if you're running in the cloud? And so we, on the whole, were actually really excited to be using the Badass Stack and Amazon's web service. And even though we ran into a variety of speed bumps, scaling up by 3 orders of magnitude in a day, we, on the whole, were able to do this only, as quickly as we did only because we had a good tool set to work with. So cloud doesn't mean free scaling, and so the stuff that's being built in the Amp Lab matters. So the second, and this is sort of a stereotype of computer scientists, that they frequently shy away from building research products, that is, outward-facing tools that are designed for other people to use. It's sort of notorious that research code is unstable and buggy and problematic and so on. And the reason that this stereotype exists is because the thought process is that if you make a research product, then you're going to be stuck answering support emails and dealing with forum threads from angry users and fixing bugs in the user interface when you really want to be focusing on the core research problems. And all of that is absolutely true. But it also, as far as I can tell for this project, has been totally worthwhile. So we now have a data set that we believe to be unique. We're able to answer questions that we think no one else can answer. And so even though I've answered literally thousands of support emails, I think we're in a position that was only possible because we actually got onto these app stores and are supporting a user base. So there's a lot to be learned, I think, from the pain of making a product. And the final thing is that I think Carat represents a kind of interesting space in crowdsourcing. So typically you have a mechanical Turk model where you pay people to do something for you. And there's money involved in that transaction. And the Carat model is more like a contract that's a service. So we're saying, we're going to give you information that's something that you can't get anywhere else. And in exchange, you're going to run this app on your device. And there are various social science reasons why I think this model actually is better. I think there's evidence that the quality of interaction that you get from users who think that they're doing something out of the kindness of their heart or because they're getting some service in return is higher quality than if you pay people to do it. And there's some really interesting results in economics and so on that show this. And I like telling that story, so approach me offline and I'll share that with you. So this, I think, has been great. So even the users who will write us and have concerns and whatnot, they seem very positive about what the app is actually doing for them. They seem to think it's a great service. So. Okay, so right now we're focusing on quantifying and improving the confidence. So we're hoping to roll that out into the client code soon. Another important direction that we're looking at is providing an API for developers. So some of the developers whose apps have been listed as hogs and bugs were understandably concerned about that fact and wanted to understand what was going on. So they wanted to know, well, what exactly are people doing with my app? What's causing this? And so we believe that if we provide an API for developers, that we could disambiguate certain causes of energy misbehavior. So configurations of apps, particular usage behavior on the part of the users, and so on. So this is something that I think would be worthwhile for us to do and that we've been looking at for a while. And finally, I think I just want to say that Carat represents a kind of interesting space here. This is the model of deploying to the crowd and debugging in the cloud. There's nothing about the analytics that we're doing or the infrastructure that's specific to energy. We could just as easily be looking at performance characteristics. And there's also nothing specific to mobile. We could be looking at browsers or laptops and so on. I don't know if laptops count as mobile, but typically they don't. I don't know why. And so this is a kind of statistics as a service model, which you see increasingly, particularly with mobile devices, where it's difficult to get a sense of what exactly is happening once you deploy the software. And so providing that as a service is something that I think has some legs. So if you go to carat.cs.berkeley.edu, there are links to our pages on the Apple App Store, where you can download the client for iOS, the Google Play Store, where you can download it for Android, and there's also a link to our GitHub, where you can find the source code for both of the clients. So if you find a bug in any of the apps, we encourage you to fix it for us. Thank you. That's it. All right, so questions, I guess. Yeah, please.
Did you find any devices were more energy efficient than others when you were publishing?
Yes, we did discover that.
Can you repeat it?
So the question was, did you find that certain devices were more energy efficient than others? Yes.
Bring a check.
So it kind of reminds me of the apps that fall under the category of the quantified self.
Yep.
The health apps. So it seems like, have you guys interacted with any of those?
We have talked with a couple of people who do that kind of work. So the question was, I guess you had a microphone, so I don't have to repeat the question. But we have, I think it would be really interesting to do stuff with the data that you get from quantified self. So in treating this as kind of statistics as a service, we thought that providing an API where you could have your sleep monitor and your running monitor and so on, and hook these together to answer interesting statistics questions about, in aggregate, what does your life look like and how does that compare with other people? So are my sleeping habits comparable to other people who have similar running habits, or what are the relationship between these things? So yeah, absolutely, I think that's super interesting. Yeah.
Did you analyze how much energy does this app consume?
We did, actually. So this is a very common question. So we bought a hardware monitor and actually plugged it in so we could get millisecond granularity and very fine control over how much energy everything is using. And so we had one installation that had Carat running and one that, instead of whenever the user interacted with Carat, they instead interacted with the standard weather app. So this is something that just tells you how hot it is outside, in case you don't have a window or something. And what we discovered was that Carat uses less energy than the weather app. So as an app, it's extremely lightweight. It consumes almost no resources. We, from the beginning, designed it to have very little impact on particular devices. We worked very hard to do that, but this did not prevent users from complaining about how much energy it used. So we had one angry user complain that Carat was using GPS all the time and running down the battery. And we wrote them a nice email that said, Carat never uses the GPS ever, so no, it didn't. And furthermore, despite all of this effort to make it very lightweight, it seems like actually there's a lot of interest from users about getting more data and more fine-grained data. It seems like there are a lot of users who'd be willing to pay some energy penalty to get the answers that they need. And by the way, the same is true of privacy. So we worked really hard to make it so that we cannot tie the data that gets reported to a particular device. But it turns out users don't really seem to care about that, and it would be really convenient for us to answer support emails and actually have a way of looking at that user's data so we can tell them why certain things are happening. Go ahead.
So I was wondering, instead of runtime profiling the applications as a feature, as you call it, right? Why, if you just statically profile the application performance on a device by itself, and then use that as your prediction in terms of who's consuming the battery life, right? So what is the difference? I mean, why don't you just simply do this offline analysis and build that intelligence into your application instead of doing this on the device from each device?
So when you say an offline analysis, you mean running some code in a simulator or something?
No, let's say you take Facebook and you run it on an iPhone, and you understand its power consumption behavior instead of doing that analysis on a real device, on an actual device.
So you run it on an actual device, but you're trying to, okay, so I'm not sure I exactly understand, but you're suggesting the crowd maybe is not necessary to answer some of these profiling questions.
Right.
So there are a couple of things that you get by running in the crowd. The first is you get a real statistical distribution of how the app is used in practice. So the first question would be, well, okay, so you have the Facebook app installed. Well, what do you do with it so that you can try to trigger these energy bugs? I don't know what kind of usage I should be doing. And it may be that there's some particular user who has a strange behavior that they do that is going to trigger the energy bug that I'm not going to think of. So you get that for free. And the second thing that you get is you can answer questions about whether or not that behavior is normal. So it may be that you run your whatever workload that you have on your one device, and it turns out that you trigger an energy bug and things are really bad. So what was it about everything that you just did that triggered the bug? That might be hard to figure out if you only have one device. But if you have a whole bunch, you can answer questions about what distinguishes the buggy users from the non-buggy users. Those are two things you get.
So would it be accurate to say that you guys were the first group that sort of got caught by a surprise scale-up situation with the badass stack? And
I don't know. That's a good question.
do you care to share anything that you sort of got caught with first, or things that went better than expected in terms of being able to get back up and running, or anything along those lines?
So one of the problems with scaling up as quickly as we did is that you don't just hit one scaling problem at a time. And so it was kind of just everything ground to a halt, and we had to quickly figure out why. So there were certain things that were difficult for us to debug. So there were some of the Amazon Web Services were behaving in ways that were difficult for us to really get our hands into. As far as scaling up our algorithm, so making some tweaks in how we were implementing it in Spark, we have the advantage that there are a lot of smart people here who were happy to help us make sure that worked. And so that was probably the least painful part of the scale up. Yeah.
So less problems with Spark, more problems with your data center provider. That's better.
Probably true on the whole, yeah.
So can you give us some scale numbers, like how large was your feature vector, and what was the size of the database, how many rows, how many columns?
Sure. So I mean, in terms of the size of the data, even now we have a relatively small amount of data in terms of quantity. But the feature vectors can be fairly long, so they include whether or not every app is running. And there are hundreds of thousands of apps. Very large feature vectors, but when we're actually doing the machine learning algorithms, those are significantly reduced because there are certain questions that we're trying to answer. So it's not like we always take the entire vector of every possible app. We just care about the apps that a particular user is running, for example. We just care about what model of device they have, what operating systems they could potentially run, and so on. And so we're not going to look at the relationship between iOS 5.11 and if the person's running a Galaxy S2 or something.
All right, last question.
Okay, with regard to the actual inferences that you're making, based on your talk, it seemed like the primary set of inferences are just comparing these expectations. In particular, you look at my device and you say, okay, what's the set of apps I have running, and then you compute the expectation under sort of that regime on my device, and then you compare it to the expectation across other users who are running similar apps. Is that true? Is that basically the core of the inference that you're doing?
I mean, comparing expected values of conditional distributions is at the core of what we're doing, yes.
Okay, and so how do you deal with the fact that you're unlikely to have any particular two users who are running exactly the same apps, right? So you somehow need to generalize across similar sets of apps. How do you deal with?
Right. So we're not conditioning. So when I rephrased and said we're comparing conditional distributions, I avoided saying that we're looking for sets of similar apps, because that's not currently what we're looking at. So we're now mostly just saying, this app is running or it's not. This app is running on your device or it's running on another device, and so on. So we're not trying to, well, I don't want to say we're not trying to do clustering, because we are also looking at that. But the core of what we're computing for users now does not require us to characterize what sets of apps count as similar, and we don't require any kind of overlap for that.
So in some sense, treating apps independently of each other, basically.
Yeah, that's right.
All right, thank you very much, Adam.
Okay.